I started reading science fiction in about 1958. That's 60 years ago. I read roughly 100 books a year, and I've collected them. So I've got a broad spectrum. Now, they're not all science fiction, but a large chunk of them are. I've got a broad selection of science fiction authors that I have read over the years. And some of them were great. Some of them were okay. A few were really bad. In my collection of authors, I've got 13,335 of them in my card catalog right now. And I've got a rank 1, 2, 3, 4 to 6. 6 is, don't ever buy that again. 5 is bad. 4 is what most authors are. 1 is like an A+. There are only 224 in that category, and that includes people like Shakespeare, Aristotle, Heinlein. You know, we're in a select, that's 1.7% is in that category. Guess where Catharine is? Right now, well, in the old days before I started, it was an old boys network. I don't think there was a no girls allowed sign. I think it was just assumed. And then after I started, it was really dominated by men. There were a few women running around who had pseudonyms, so we didn't know that they were women. But it was mainly dominated by the men. Then a few years ago, I don't know, 10, 20 years, it's a few to me now, something happened, and the best science fiction authors of the time were 4 women. Catharine Asaro is one of those 4 women. If you haven't read her, you need to start. If you have, you know what I'm talking about. And this is Catharine Asaro. Thank you.
I had no idea you felt that way. Yeah, I was actually told I should change my name when I started, because I write hard science fiction, which is science-based. And people said, no, you have to have a man's name. And I said, why? And they said, because everyone expects men to write hard SF. And I said, how is it ever going to change if people like me don't use our own names? So I was very ornery, which can dismay your publisher, but I'm pleased to say I have a very good publisher, and they're the ones who provided all the books. I have some good news about Theme 4. If you notice in the schedule, there's 2 empty spaces at the end. That was because 2 of our speakers were sick, got sick at the, one of them wasn't sure he could come, and he realized as we got closer to the date that he wouldn't be able to make it. And the other one was hit with bronchitis, almost turning into pneumonia last week. However, we were able to arrange a Skype session for Alan Steele. He will be coming into us via Skype. And we already knew David Brin was going to do that because he couldn't come to Oak Ridge this week. But he did agree to give his talk over Skype. And so Alan is also going to do it. He'll be coming on. We're going to move my presentation of the awards and this Theme 4 synthesis to the end and put Alan. Alan Steele will give his talk in there. And also Arlen Andrews sent me, he prepared everything. He was very disappointed he couldn't come. So he sent me his presentation, and I'll read what he wrote for it. Okay, well, I'm going to introduce this idea of it's not just using science fiction to think about what the future might be. I mean, a lot of science fiction, we're saying, well, what if? And then we play with the what if. And for hard science fiction, which is my favorite, kind of my area, subgenre, we start with known scientific facts and say, okay, what if we changed one thing? What are the extrapolations of that? And it really works for inspiring new development in science, too. For me, the most exciting things that I ever did for NASA was something called the Breakthrough Physics Propulsion Workshop, of which I'm pleased to say we have the founder here, Mark Millis, to give a talk when I'm done. The idea of that was to try and develop new physics based on ideas of what if. Try to develop feasible new physics. And I'll never forget at one of the symposiums, the first thing Mark did was put a picture of the Enterprise up in his overhead projection. The reason I like that is because science fiction had always inspired me to think about the stars. I liked reading it so much I wanted to know, could we really get out there? And I don't even know which came first. I mean, I think I was born dreaming of going into space. So did I like science fiction because it supported that dream, or did that dream grow out of my love for science fiction? Well, we hope to certainly inspire current generations, not only of students to be interested in science and the public, but to inspire people to think of new ideas in science. And that's what the idea of this, what we're doing with this theme is, how can we inspire and think of new physics that will take us beyond? And one of the reasons that I picked, this is from NASA, it's a composite. That was definitely photoshopped. I like it for a couple of reasons. One is that if you look how close together everything is, those are the places we want to visit in the solar system, right? That's the planets. We got some asteroids in there, a comet. It's the places we want to go, including Mars, which I think, if anything, that this symposium has showed us is that, yes, it is feasible. If we have the will, we do have the technology to develop and to get there. I like that these are so close together because it stresses the fact that there are really larger distances that we want to visit, too. We also ultimately would like interstellar travel. And of course, those distances are much greater, and it makes the distances in our solar system seem very small. So I was encouraged by this picture. There was one other reason I liked it, and that is this little guy right there. It was demoted. It was demoted, no longer a planet. So Pluto's not a planet, but it's included in that composite. Okay, so what I'd like to do for my talk is give you an idea of what do I mean by using a what if, science fictional ideas, to inspire us to go farther in science. So the idea, the theme of this talk is using science fiction to imagine new science. Okay, I'm going to talk about one specific case, which actually led for me to a paper in the American Journal of Physics. The idea is to extrapolate. So we want to start with a solid foundation of science, what we already know, ask what if, explore the ramifications, change one thing in an equation. What does that mean physically? And this is the amazing thing about the synergy between mathematics and engineering and physics. If you play with equations, if you start with something that physically is realistic, like quantum mechanics, we start with the Schrodinger equation. When Schrodinger said, what if I could describe matter using a wave equation? That was a huge jump of, you could say, creativity, genius, an extension, an extrapolation of what we already knew. All the mathematical machinery was already in place. When he said that, and he proposed a Schrodinger equation, all that most of the initial workers on quantum mechanics did was solve equations. It did all these things, found solutions, found all these complex, abstract mathematical functions, did work on those, said, well, the math implies this and this and this, and they finally got down to, based on all this math we've done, this is what we predict the energy level of an electron is in the hydrogen atom. They were dead on correct. It was, I think, was it 13 point, I don't remember now. What, 6? 13.6 electron volts. They got it, dead on. And in fact, quantum mechanics has turned out to be one of the most successful physics theories of all time. It started with a what if, and then they looked at the ramifications. If you start with something that's physically a good model of the universe, the math you do on it, which tells you the ramifications, will probably lead you to something that's physically correct. You just have to figure out how to test it. Quantum mechanics was bizarre and strange and sounded very science fictional, but it was easy to test. We knew how to measure the energy level of the ground state of a hydrogen atom. Current day physics is not so easy to test. In fact, some of the theories take the energy of a substantial portion of the universe to test it. So we have to figure out new methods of testing. Okay, and enjoy, of course. All right, so I would like to talk about the universal speed limit. We have a problem. We can go to Mars in our lifetimes. We can actually get there pretty quickly. In fact, I was very encouraged by what I heard of some of the talks, that just how quickly we can get there if we can, put together the correct technology and get a good plan in place. We can't get to the stars quickly in a feasible amount of time because of the universal speed limit. Physics says we can't go faster than the speed of light. However, what it actually says, if you look at the mathematics, is we can't go at the speed of light. Okay, so I want you to think you're on your bicycle because you're very healthy and you're riding to work. And you're faced with this tree that is infinitely high. That's essentially what the speed of light does to us. Your energy, for example, relative to, say, Earth, if you're going at closest speed of light, is approaching infinity. And that's why it's relativistic physics. It's always relative to another reference frame. So essentially what you have is, this is your energy, okay? And when you reach the speed of light, we can never reach it because our energy becomes infinite. It's the old energy equals mc squared. M depends on your speed. We don't notice that in real life because you have to get within 10% or so of the speed of light before it becomes significant. So if your energy is infinite, you can never go the speed of light, and a lot of other things. I mean, probably you've all in here had modern physics, right? Do you remember special relativity? You have things that appear to be length contraction, time dilation, and they all reach, at the speed of light, it becomes impossible for an object with mass to travel that fast. Photons can, but they don't have mass. So we can't go through the speed of light, so we can't go faster than the speed of light. But what if we could go around it? What if you could leave the road and go around that tree? The reason I asked this question, when I was started to write science fiction, I was in grad school. I was getting my doctorate in atomic and molecular physics. And I was really bugged because I wanted to write a galactic empire, right? And I thought, I can't do this. I'm a physicist. I'm deeply disturbed. I'm greatly traumatized by the fact that you can't go faster than the speed of light. So I said, well, if I figure out something that at least mathematically works, then I'll feel better, right? it was more, this is fun. Well, it turned out that, and I'm going to go through very briefly what the mathematics were. It works enough that the American Journal of Physics published my paper describing how you would apply this mathematical technique and what would the ramifications be. They did tell me, make sure in your abstract you say this is a mathematical game. It's a thought experiment. Because they didn't want people saying that the American Journal of Physics says we can go faster than the speed of light. So I made sure I said that. And it's a very simple idea. I looked at special relativity. This would, to really make this more complete, I would need to extend the ideas to general relativistic physics. But it's actually very simple if you look at special relativity, which doesn't involve, for example, accelerations. So all you have to do to circumvent the speed of light is make your speed complex. It has a real component and imaginary component. Do you remember back in I think it's 5th or 6th grade, you get this. They tell you when you're young that you can't take the square root of a negative number, right? But they lied. It's not true. You can take the square root of the negative number. It just has no physical meaning that we know of. It's called an imaginary number. That's why we call it I. So this is all I did. I said, assume that the speed of an object has a real part, which is the speed we see, like when you're driving down the freeway, right? Your speed is 60 miles an hour. That's the real part. And then assume it has this imaginary part as well. That's the one what if. And I took that and I plugged it into all the equations of special relativity. And it completely changed the physical predictions. The problem with the equations of special relativity is that when V equals C, there is a square root in there that becomes 0. Okay, you have a ratio of V over C, right, squared, minus 1. All right, well, if V equals C, you have 1 minus 1, it gives you 0. And that square root, which equals 0 when the speed equals the speed of light, appears in, everywhere in special relativity. Anything you're calculating, almost all of it has in some place, it's called the gamma function. Well, if you divide by 0, things go to infinity. If you multiply by 0, things go away, so they no longer exist. Either of those is a big problem, right? If you're in a spaceship, you don't want to stop existing and you don't want your energy to go to infinity. This takes it away. Okay, your real part can be equal to the speed of light, and there's no infinities because the imaginary part makes this gamma function non-zero. And it's essentially like leaving the real axis, that's the road, and going around the tree by going into the complex plane. And the ramifications are wonderful. I mean, it was a lot of fun to play with it. Also, it implies all sorts of things, like you can't go slow. If you're going faster than the speed of light, you can't slow down, right? Unless you go around again, because now you have the infinity, this pole, we call it a pole in the complex plane. It's in the other direction if you're faster, because it's going through the speed of light. That's the problem. So I wrote up this paper, Complex Speeds in Relativity, American Journal of Physics. It was April 1996. And I'm a little bit embarrassed to say that I was writing this paper while I was working on my first novel. And the novel kind of took over. And, it was one of those things where I always intended to finish the paper. And the reason it got finished was my publisher, my editor said, well, marketing says if you get that thing published, they can use it to market your book. And I said, oh, all right, I'll finish it. So I may be the only person who finished a paper because marketing and their publisher said their science fiction book would do better. So for me, I was done with that particular part of the problem because I'm a theorist. What I created was a mathematical game. It's a game because what does it mean to have a complex component to your speed? Well, this is where the new physics comes in. And that paper got me invited to be a speaker and later the chair of a session at some of these breakthrough physics propulsion workshops. Very similar to this, except they bring in people to talk about how can we come up with new physics to make interstellar travel feasible. And the people were interested in, did I have any ideas about how you could test this? So I thought about it. There's a long history of use of complex numbers in physics, right? It's just that you have to figure out how to turn the whole machinery of complex analysis to produce a number you can test. For example, the index of refraction, if you look at the complete physics that describes the index of refraction of a material, it has a real part and a complex part. The real part is what we normally think of as index of refraction. The complex part does have a meaning. It has to do with how much the attenuation of the wave, a light wave, is attenuated in the material. In quantum scattering theory, there's all sorts of these things called poles in the complex plane. They correspond to places where the energy is resonant. By resonance, that means it gets big. Or in scattering theory, it means that it's captured by, the thing doesn't scatter, the particle doesn't scatter off the other particle, it's captured temporarily. So I was looking at this theory and I thought, they resemble what you get with special relativity. And it has a meaning, for example, in complex scattering theory, the imaginary part is the width of the scattering resonance. So the next step for this would be, if we actually wanted to see if it was more than a game, would be to find something that you can measure. And to do that, it is a long tradition in science fiction, in science, to say, can I compare this to things that are already scientifically known? So that's where we hope that scientists would go with some of the ideas. If this what if is reasonable, can we compare it to something that's already known? And it's a lot of fun, at least for me as a writer. And hopefully it will someday inspire new generations of physics. See, this is the thing. My only problem with my own work actually is that it assumes if special relativity is true for slower than the speed of light, it's also true for faster than the speed of light. But that could be like assuming classical mechanics is true for objects moving at classical speeds, so shouldn't it also be true for objects moving at relativistic speeds? Well, it's not. It's a new physics. You can show how they correspond, how you go from slower speeds to faster speeds, how the theories change from classical theory to relativistic theory. It's the same thing for quantum mechanics. Yes, the physics for large objects like us, we don't diffract when we go through doorways, but it goes evenly into, it's called the correspondence principle, to the physics of what happens for atoms and molecules. But it's a completely different theory. And my guess is someday we probably will figure out what goes on in realms of faster than the speed of light. But if we do, it's probably going to require a new physics. So, I'm optimistic, but still on the fence for what that'll be. So I think it's a wonderful time to be alive. I suspect we're going to see a lot of advances in that area. I think I'm running, how much time do I have left? About 1 minute? All right, let me finish up. I was going to talk about artificial intelligence. I don't have time. Will remain human. Yeah, there's a lot of stuff. If you want to get one of the books, this is the most recent. That's the one they brought. Anyway, I hope that for seeing the talks given by the various people, that maybe they'll inspire some new ideas for this group of brilliant people we have here today. And thank you very much.